it to him.
Oh, you did?
Yeah, like 2 days ago or something.
Oh, that's nice. All right, yeah. Let's do it.
Okay, so playing Atari with deep reinforcement learning from the original DeepMind guys. We present the first deep learning model to successfully learn control policies directly from high-dimensional sensory input using reinforcement learning. So this is important because it's the first time it's from images, right? From pixels. The model is a convolutional neural network for the images, trained with a variant of Q-learning, whose input is raw pixels and whose output is a value function estimating the future rewards. Okay, so that's the only neural network in this. There's one neural network, it's a convnet, and it's going to take in an image and it's going to output a Q value, which corresponds to estimating future rewards. We apply our method to 7 Atari 2600 games from the arcade learning environment with no adjustment to the architecture or learning algorithm. We find that it outperforms all previous approaches on 6 of the games and surpasses human expert on 3 of them. So out of 7 games, they beat 6 of them with the same method, with no adjustment of the architecture or learning algorithm. So that's pretty important. Usually before this, reinforcement learning was very like hands-on, handcrafted features specific to the game. This doesn't do any of that. It doesn't cheat. Okay, so this is what the games look like. Let me zoom in because we're gonna have to do that anyway. So this is Pong. This is Breakout, where you break bricks at the top, and it's like one person Pong. This is Space Invaders. This is some kind of submarine game, and this is some kind of dodging game. Okay, so this is the algorithm, and this is pretty much. I mean, we can go through the rest of the paper if you guys want, but it's all kind of here. It's all kind of summarized here. So algorithm 1, deep Q learning with experience replay. So we're gonna initialize a replay memory buffer D, the capacity N. N is usually 1,000,000. So you're gonna store 1,000,000 previous transitions. The replay memory is gonna store transitions of the game. What's a transition? A transition is like a state, which is like an image, and then an action, and then an observed reward and a new state. So this tuple right here, phi of j is the state, a of j is the action, r of j is the reward that you observe from taking action aj in state phi of j, and then you also observe phi of j plus 1. So this is kind of the basic reinforcement learning loop. Let me just cover that real quick. Is this good? Yeah, so the agent takes actions which affect the environment, and the environment sends back states and rewards. So this is the loop that you go through. So there'll be like a while true, you do this basically until you like error out. Or not error out, but like until you until the session terminates, until you lose the game. Okay, so initialize action value function Q with random weights. So that's just initializing our neural network Q with random weights. Straightforward stuff. And then, so for each episode 1 to M, do initialize sequence S1 equals to X1 and preprocessed sequence phi of 1 equal to phi of S1. So what's happening here is X1 is the first image, and the preprocessor just stacks the images. So if you're thinking about playing Pong, the reason you want to stack images, instead of just if you just had this image when you were playing Pong, you wouldn't know which way the ball was going, right? So instead, what they do is they take this image plus the previous one, and it's actually the 4 previous images. So this one plus the 3 previous images gives you a stack of 4, and then you can see the velocity of the ball.
The quick news update: Mojo is supported with PyTorch right now.
Oh, sweet.
Leave that till after.
Yeah, go on.
Okay.
Don't.
So,
ideally, don't interrupt. Don't interrupt with things like this. This is nothing related to what we're doing.
Yeah, my bad.
So this is just a pre-processing step where we're stacking images, okay? There's also, it's not just stacking images, it's also grayscaling them, making them 256 by 256 or 224 by 224, whatever the resolution is for the ConvNet. So it's resizing the image, grayscaling it, and stacking 4 images. So then with probability epsilon would be something like 0.01. So with 1% chance, we select a random action. So this is like our exploration policy. It's kind of like we're going to explore one in every 100 times we're going to take a random action. And that's just to guarantee convergence of this algorithm. Without this line, this algorithm isn't guaranteed. There's no proof of convergence. In practice, like epsilon starts off high and they decay it to 0 or something really small. Anyway, if it's not that 1% chance, we're going to select the maximum Q value function. So remember the Q value is the expected rewards for that state and taking that action. And theta is just the parameters of the neural network. So for that particular, so we're going to take the maximum over all actions. So what this amounts to in practice is there's 2 ways to do it. You can do a neural network that takes in an action and a state and produces a Q value, or you can do a neural network that takes in a state and produces 4 Q values, or however many, or 5 Q values, however many actions there are. So actions are discrete. Actions might be like move up, move down, move left, move right, and then press A to jump, press B to shoot flower power or whatever, whatever it is. So the inefficient way is to just iterate through your Q network and do one action at a time and get the Q value and then take the max over all Q values. The efficient way is to just do one pass through and get however many actions you have values, and then just do the max of that. Okay. So we selected the optimal action according to our neural network because it has the highest expected rewards. Then we're going to execute that action in the emulator and observe reward RT and image XT plus 1. So this is just standard. We're going to take the actual action. Actually, this is like the actual interaction with the emulator. Everywhere else, there's no interaction with the emulator. So then we're going to set ST plus 1 to ST, AT, XT plus 1, and preprocess blah, and store the transition. So we're going to store the transition in the buffer D. And then for the learning part, we're going to sample a mini batch of transitions in D, which again is like size of 1 million. And if it's terminal, we're just going to output the reward as the target. So this is us setting the target. And then if it's not terminal, we're going to output the reward plus gamma, which is a decay factor, usually something like 0.99 or 0.95. This sort of depends on the game, but all of the games are sort of of the same temporal action. Basically, if you have longer dependencies in your game, then you want a larger gamma. And if you have shorter time scales in your game, then you want a smaller gamma. So you might do so for a game like Tetris, you might do 0.99. For a game like Mario, you might do 0.95. That's not the best example, but yeah. Anyway, so what's important to note here is that we're again taking the max over all actions, but this time of the next state that we arrived at, if it's non-terminal. And importantly, this gives us a better guess of the expected rewards. So this itself is going to be a reward. So you can expand this out further. You can sort of see it as Rj plus gamma times Rj plus 1 plus gamma squared of Rj plus 2 plus gamma cubed of Rj plus 3 plus gamma to the 4 of Rj plus 4, and so on. So this is, again, an expected return on rewards. But notice that it's a better guess than the guess we got here. So it's a slightly better guess because we have this reward information and we have this state information. Okay? So this is a sort of bootstrapping process. What we do then is we perform gradient descent on Yj of the original, of the transition of Q of phi j aj theta squared. So mean squared error loss. So yeah, that's pretty much it. We can look at equation 3 real quick. So this is the target, and this is the Q this is the predicted, and this is the derivative or the change, and yeah. How's this different from supervised learning? So in supervised learning, the data set is static, whereas in reinforcement learning, any action you take is going to affect which state you end up in. So it affects what your predictions are at the moment affects your future data set, right? And instead of having perfect targets that tell you exactly like what the correct prediction is, you only have this bootstrapping mechanism, which might be why reinforcement learning is so sample inefficient. Usually it takes like 1 million steps to get results from this algorithm, like at least 1 million time steps. Yeah, does anyone have any questions?
So when you say 1 million time steps, what is that exactly?
That's like a game time step.
Okay. And they're playing Atari?
Yeah.
Okay.
Can you show a PyTorch implementation of this?
Of what?
Of the paper we're looking at? Oh yeah, you're implementing it.
Are you talking to me?
No.
Yeah, so I implemented it for Tetris, which is actually a pretty hard game. If you look at the literature for Tetris, it is not like great. Usually they cheat by telling the key difference is they usually cheat by telling it how many holes there is as a feature. So they'll say like, oh, there's 3 holes in the current structure, and from this, the algorithm learns very quickly that holes are bad in the structure, and it learns to avoid them, and it learns fast. But if you don't do this, then it's kind of a hard problem, just because of the geometry of it, and the amount of time it takes to get feedback. And it just takes a long time to like discover a line clear, like to randomly, because at first you're just doing random actions, trying to see what works. You might realize that, building flatter structures is better because once you get a terminal reward, you get no more rewards. So in this equation, you'd get R of j instead of R of j plus an estimate of future rewards. And this is going to be positive usually. And so this R of j is gonna be less reward, and you're going to realize that tall structures are bad, flat structures are good, and then you're going to eventually discover a line clear. And I did have an implementation that in NumPy that solved 2x2 Tetris, where all the blocks are just 2x2 blocks. But I haven't been able to get this PyTorch implementation to do the same thing. I can show you guys it running after.
Where's the actual algorithm?
Yeah, so the actual algorithm is so let's scroll to the bottom. So if rendered, then process it. This is important. This is like user input. So process DQN input, then apply gravity, then clear line, then draw boards. So all of the stuff is in a process DQN input, I believe. So here, here we have the prediction. So this is the prediction line is getting the Q values in one go, because this is the more efficient version. This is the prediction, and then here's the argmax that we see over here, max overall actions. Then this is just translating the actions to moves in the game. So 0 is move left, 1 is move right, 2 is move rotate, 3 is move down, and 4 is move drop. Then it takes the targets. So what we're gonna do is a little trick. So notice that when we go through the neural network, we only took one path, right? There's this neural network, because it's the efficient version, it actually gave us a Q value for every. It gave us a target for, or like a prediction for every possible action, right? So it gave us 5 Q values. But we don't want to backpropagate against 4 of those because we didn't take that path, right? So because we didn't take that path, we're gonna set Y to be the copy of the predictions. So we're going to take the predictions, set it to Y, and then just change the path that we took, Y at move, right? So the target is just going to be changed for the move that we actually took. And then we're going to see what better estimate of the Q value we get. There's no epsilon here, I think. I didn't do epsilon. I was trying to do other exploration methods other than epsilon greedy exploration. So here's the reward. Here's gamma. Here's the argmax again of the later state. Because we took, I I think this options at move calls one of these functions, whichever move it is that it considers optimal. So we executed this action, so the board changed. So yeah, we just changed the target at the move, and then we backpropagate, and that's it. That's it for the algorithm. So another issue, feature that this doesn't have is the experience replay buffer. Since I want there's no experience replay buffer. It's just
can you show?
We're just gonna act.
Oh, go ahead.
We're just gonna act immediately on. We're just gonna backpropagate on the thing we saw immediately, and then forget about it.
Can you show like a completely native implementation in PyTorch, like not in a game?
Sure.
Like game agnostic.
Game agnostic. Sure, sure.
I think there's a tutorial right there.
Sure.
Oh, but this is
so the thing about, like, you still have to, it can't be completely game agnostic because there's going to be like a different number of actions that you're going to, you're still going to have to specify like the number of actions and the size of the input image, right? So like it depends on the controls that you have. So it's game agnostic, but it's not controls agnostic, if that makes sense. It's also not like image size agnostic, right?
Mm-hmm.
So this is their neural network. Just linear with values. So here they don't use a convolutional neural network because the input is like a vector of numbers. It's like the position and velocity of this thing and the angles or something like that. It's not the image. So this isn't based on an image. So that's why their neural network isn't convolutional. Then they're going to select action tiers. If sample is greater than epsilon threshold, then with torch no grad return policy net state max blah, else return a random action. Okay, so this is the epsilon greedy part. Let's see, training loop. So this is where they update their target expected state action values, next state values times gamma plus a reward batch. And they use smooth L1 laws, and then they backpropagate. Is there anything we're missing?
What's the Huber loss? Go back.
Can you share that course?
What's the Huber loss?
I don't know. I think it's specific to might be specific to this game. I'm not sure.
I think. Can you? Yeah. Could you share it with Zach for a sec?
Sure.
Yeah.
Share it. Put it in the. Did you post this in the papers channel?
No.
The paper, I mean.
No.
Oh.
I don't think I did.
Could you please?
Yeah, let me do that. projected being 2. That's surprising. Yeah, it doesn't look like I have it posted. Yeah, let's look at this Huber loss. It looks like mean squared error, but then if A is less than delta.
The Huber loss is the convolution of the absolute value function with the rectangular function, scaled and translated. Thus, it smoothens out the former corners at the origin.
This is actually pretty fast. So yeah, toy task is definitely a lot faster. When it's just a vector of values, but like from pixels, it's usually a lot of episodes. And then each episode is like...
How can we implement this in a transformer?
For reinforcement learning from human feedback.
Then how do we create a reward model?
A reward model. Mm-hmm. So in the case of, for example, in the case of my implementation, I did reward. I just rewarded +1 when it's a line clear, and otherwise nothing. I think that's the only place. You can also penalize it for like losing the game, but it's kind of already done with the terminal state, right? So that's not really necessary. But yeah, usually the reward model is like in games. Usually it's the score. So in Tetris, this sort of adheres to that. In Tetris, you'd get an increase in score every time you clear a line. And so that's what I do. For them, let's see. For them, it's just the duration. So they add +1 for every incremental time step, and then the environment terminates. So it's just the duration of the episode. So this is often used too. It's pretty good. So they just do +1 reward for every time step. So for if you wanted to cheat in Tetris, you could say, if there's holes in the structure, then you penalize it. You decrease the reward. And let's see, they use a gamma of 0.99. At the start, epsilon is very high for exploration, 0.9. And then epsilon at the end is 0.05. And that decays over 1,000 time steps, I guess. I don't know what tau is. Tau is the update rate of the target network. Okay.
I see.
So you can often shape the reward more and more. Like you can cheat arbitrarily much, right? Like you can shape the reward function to be very specific to a task, but usually the reward is just a number, regardless of how fancy of a function it is. It's just a scalar.
Can we look at some multimodal reinforcement learning algorithms, like for transformers? Like how can we make like a model, like a reward model for like Cosmo? I mean, GPT-4 now is like kind of like GPT-4. The vision part was trained with some form of reinforcement learning. They created a vision reward model. To my knowledge, look at that multimodal transformer for offline reinforcement learning. Awesome, multimodal reinforcement. Wow, those are some good links. Yeah, I'm very interested in how OpenAI trained GPT-4 to be so good at vision.
We could look at the GPT-4 technical report.
I mean, we could, yeah, but I don't think they mention anything there. They've been very, very secretive about that.
Called pixel space diffusion, bros.
Pixel space diffusion?
Yeah, I came in here to talk to you about something else, but I'm going to wait until your thing is done.
Oh, yeah. What do you mean pixel space diffusion? Like,
you can look up pixel space. That's right. You can look up pixel space diffusion if you really want to know what they did for making the image model outputs look so good, as opposed to latent space diffusion.
All right. Do you mean for DALL-E or do you mean for GPT-4 Vision?
Oh, I thought you guys were talking about DALL-E 3 because I was looking at your DALL-E 3 repo.
Oh, no. I mean, no, we're talking about GPT-4 Vision, but I am also curious as to the model architecture for that. Yeah, I'm very. Have you used GPT-4 Vision? It's really good.
Yeah, I have, but I haven't seen the architecture or research papers.
Do you think they're using reinforcement learning for the multimodal part stuff?
You mean like RLHF? Because lots
Yes.
of people are doing RLHF. There's something like unexpected about that.
For multimodality.
Yeah, I mean, they've been OpenAI has been doing RLHF, and I'm not surprised if they're doing that for multimodality as well.
I see. Um,
But because they literally have teams of people like that are just sitting there, rating outputs, and from some place in like India or whatever, there's some news that talked about the people whose job it is to literally sift through the outputs.
Yeah, I think there's like a team in Africa that does this.
I think if we could implement like RLHF, however you say it, learning from human preferences in vision, I think that's how you get a new state-of-the-art vision language model.
So we can definitely do
You
RLHF.
got to train a separate model to be the critic, so that you don't get like the issues with regular RL. So first you got to train a critic model.
I see.
Like regular RL is not stable during training. That's why they use a separate model that's trained to be the critic, so that you get more stable feedback.
Yeah, we could definitely do it. I don't know about getting state-of-the-art results because the scale of the model would be much smaller than OpenAI's, but we could definitely train Mistral with RLHF for whatever, like open interpreter purposes.
And then you're going to have to do some sort of cross-attention between whatever your image encoder is and whatever the text encoder is. Assuming you didn't already know that.
Yeah, or I think maybe no wasn't talking about like maybe he just was talking about text, not necessarily vision. Is that what you meant? Is that what you meant?
I thought he meant trying to turn the Mistral large language model into a multimodal model.
Yeah, that would be interesting. Yeah, that would be very interesting. I think some people are doing this now. I saw somewhere that some team is trying to do this right now. It wouldn't be that difficult. You just need to modify the tokenizer, add a special multimodality token, images or videos, and then you would embed the embeddings of the multimodality inside of that token inside the tokenizer. Then that would be passed in as a unified yet distinct token inside the model. And this is how Cosmos, Palmy, and like some of the other models are working now. They just have a token where they have a token that's just for multiple modalities, and inside that token, there's just embeddings.
Well, I mean, maybe some people are doing that, but it seems like maybe the way that you can do it if you don't want to train from scratch and just essentially bootstrap something on. But all of the really good models are trained with cross attention.
So we looked at a paper like yesterday, I think, or 2 days ago or something, where it's just an add-on. Like the they're sort of modular, the language model and the vision component that translates the image into something the language model can understand.
Yeah, I mean, if you get blip, right? Let's say hypothetically you get blip and you get Mistral, and you want to glue them together, you can use that method. But most of the models, multimodal models that aren't just duct taped together, are done with cross attention.
Do you think we could use DQN with that?
Yeah, I think so.
How would it work?
I mean, I don't know. The PPO method that they use is like policy gradients based. So that would be quite different. I'd have to think about how to adapt DQN to the language model situation. It might be tricky.
Would it just be better to use PPO?
Yes, probably.
What's better than PPO?
There's like more elaborate methods. There's like there's like other advances on TRPO, trust region policy optimization that exist. But yeah, I don't know the details. I don't think like it's that big a deal to try and to just use proximal policy optimization. I think like where we could really benefit is from custom RLHF responses. So like when the model makes an error in like what it should caption the image to be, you know, it might say like, oh, I can't caption this image because it's of Barack Obama. We could just have the actual caption, so we can have different, like we can have a different style of safeguards, for example.
It's a very long system.
I heard, I was seeing in some of the recent papers that DeepMind was using some other reinforcement algorithms. I forgot the name, but in RoboCat's a really good robot paper, by the way. Basically, the RoboCat can understand multiple modalities, but it could also generate its own data. So it's kind of like an endlessly self-improving loop. They say that they use chain of hindsight. I don't know what that means. I don't know if it's like a prompting technique or if it's a reward reinforcement algorithm. But they use something, a form or an algorithm I've never seen before. We demonstrate the ability. Yeah, DeepMind has been putting out some pretty interesting reinforcement stuff. I think they're undoubtedly the best now. And also, what was it? OpenAI has another reinforcement algorithm that's really, really good. What was it? It was something math. OpenAI. Let's verify step by step. This reinforcement algorithm is really, really insane. So they have an equation, like a math equation, right? And they don't just train it. Oh, what is this? Yeah, so it is
This is
so it is an algorithm.
hindsight experience replay. Yeah.
Oh, what? I didn't see that. That's what they're using in RoboCat?
Yeah. Or at least they mention it. RoboCat is based on Gato and VQGAN encoder, which is pre-trained on a broad set of images and it enables fast iteration. We specify tasks via visual goal conditioning, which has the desirable property that any image in the trajectory can be labeled as valid hindsight goal for all time steps leading up to it. So yeah, it looks like they use it.
I didn't know this algorithm existed. I think I'm going to try and implement this. Yeah, because I think this would be useful.
You should
it looks like they use goals,
by the way,
or something.
Be aware, by the way, that ask Lucas Nestler if you don't believe me, right? But Google has intentionally published misinformation specifically to try to get their competitors to waste time on things. And I don't know if this is one of those models, Gato. I know that one of those. I'm going to look up Gato real quick because I was underneath the impression that they faked the results.
Well, people fake the results all the time. That's why I'm such a big. That's why I'm like an open source radical extremist, because that's the only way to really verify any results now. I mean, because having a paper, you could just talk about a bunch of shit in a paper, but that doesn't make it actually real. What makes things real is a reproducible experiment. This is like the whole foundation of science. If there was no experiment, there was no science. So
I'm not trying to make some point about that. I'm just saying specifically that specific model, Gato, I think was already claimed by Lucas as having been faked. But so I'm just saying whatever is in there, you might want to take it with a grain of salt or something like this.
Yeah, Gato came out last year, I think.
Yeah.
Yeah, Gato was cool.
Lucas tried to re-implement it for John Carmack, and I think he told me something about it being faked.
But how could it be fake though? I mean, like they could fake the results.
The results are faked. Is what I mean. Like their performance faked, and the research paper was faked.
I mean, looking at the architecture, I don't think I think it could actually produce the results. I don't think it's like impossible.
I'm just telling you that Lucas has tried to reproduce many papers and has the training budget to do so, and has told me in the past that Google has been publishing misinformation in his papers. So just be forewarned. And take anything in the papers with a grain of salt. This is like a well-known tactic in corporate behavior to trick your competitors into spending lots of time trying to do things that aren't going to work. The Soviets, for example, and the Americans did the same thing.
I appreciate your concern.
So this is interesting. Hindsight experience replay seems to sample a random goal. A goal is like a state associated with an indicator function of whether you've achieved that goal or not. So it tries to get to a specific state, even if it's not like the task state that is like the original task. And then it seems to try and fulfill those, to try and get to those states. So it sort of learns how to control before it learns to achieve the global task. It learns how to achieve like subtasks.
Where do I put screenshots from Yannick's Discord? I was going to screenshot Zigzag's response there as research. So this is with regards to Gato. And we did discuss this last year.
So this algorithm probably makes a lot more sense for control tasks, like getting a robot arm to pick up a blah, than it does for language agents. Just because with the robot arm, there's so many time steps and so many states that aren't like the winning state. But in particular, you have so many time steps, whereas ChatGPT can often just like one or two shot to the task. So maybe this isn't applicable.
Also, this is like for continuous functions are different than sequence functions.
On the other hand, Gato RoboCat can do language, right? Can it do language? No, I'm thinking of Gato. Actually, no, it says foundation agent, but for robotic manipulation. But yeah, it's definitely interesting. It doesn't look that bad to implement. Again, like when I implemented DQN, it was just from the algorithm one section, and I think you can do the same thing with hindsight experience replay.
How do you think they're doing it with RoboCat? Like what is the environment for RoboCat? Is it like like what would it be?
The environment is the real world, right?
Mm-hmm.
And then they have a camera set up looking at the robot arm, and then actions are movements of the robot arm, and rewards are 1 if the task has been completed and 0 otherwise, I think they said. Or maybe that was in her paper. Let's... Yeah, they don't really need like a dense reward function because they have the goal strategy. So whenever they accomplish a goal, they get reward, I'm guessing.
What would the code for this look like in PyTorch? I try to implement it, but it's not good. There's no RL at all. I know what the model looks like, but I don't know what the RL would look like. I haven't done too much RL stuff. Perhaps the hindsight. Should find an implementation for the hindsight. Oh. Connection. Okay. My connection isn't good. Can you hear me? Yo.
So this looks like only part of the algorithm. At least it's not performing the optimization, it looks like. So for the optimization, we have to look in
I think it would be pretty valuable if there was like a plug and play version of this where you just plug in your environment and it just works. Because RL is typically very custom. You have your own environment, you have your own constants. Things get very restrictive.
it says, oh, this has actually a lot of stars. And it seems to work. Okay. Okay, fine.
Isn't this the one that you were just looking at?
Yeah.
Oh.
I was just checking the Google results to see if there's like anything else that's like there's this one. They have a DQN with her.
How would DQN fit in?
Her seems to just possibly modify the reward function. So a DQN would just benefit from that. Like you can still use goals and then achieve them and then get a reward based on that, right? Look at the paper.
The DeepQN network, is that just a bunch of linear layers and the ReLUs?
For when there's no image, yeah. Usually it's a small network. It's not anything too fancy. Even the original Atari paper, it's just We can look at the details of the network. Working directly from raw Atari frames, which are 210 by 160 pixel images with 128 color palette, can be computationally demanding, so we applied basic pre-processing step aimed at reducing the input dimensionality. The raw frames are pre-processed by first converting their RGB representation to grayscale and downsampling to 110 by 84 image. The final input representation is obtained by cropping an 84 by 84 region of the image that roughly captures the playing area. The final cropping stage is only required because we use the GPU implementation of 2D convolutions from 11, which expects square inputs. For the experiments in this paper, the function phi from algorithm 1 applies this pre-processing to the last 4 frames of a history and stacks them to produce the input to the Q function. There are several possible ways of parameterizing Q using a neural network. Since Q maps to, we now describe the exact architecture used for all 7 Atari games. The input to a neural network consists of 84 by 84 by 4 image produced by phi. The first hidden layer involves 16 8 by 8 filters with stride 4 with the input image and applies a rectifier nonlinearity. The second hidden layer involves 32 4 by 4 filters with stride 2, again followed by a rectifier nonlinearity. The final hidden layer is fully connected and consists of 256 units, rectifier units. The output layer is a fully connected linear layer with a single output for each valid action. The number of valid actions varied between 4 and 18 on the games we considered. We refer to convolutional neural networks trained with our approach as deep Q networks. So yeah, this is tiny, right? It's like 2 convolutional layers and like 2 linear layers. So yeah, it's absolutely like, it's not a big network. It's just supposed to run fast, so you get a lot of iterations. Because the slowest part is not the emulator. Usually, it's the neural network.
Is that the? Can we look at the DeepQN network in the repo that we were just in? I want to see what it's like.
Sure.
Yeah. So DeepQN network.
So this is.
We have to find.
Do you want the pure one?
What do you mean the pure one?
Without hindsight experience replay.
Oh, with. But you see, it's importing. Wait, it's importing. Go up a bit. It's importing DeepQN network as DeepQN. What is this? Is this another package? I want to see what that's implemented like.
Yeah, I guess so.
Can you go to the requirements.txt? Or you could have just scrolled down. Oh, I guess not. Then where's that code coming from? Oh, it could be in the same folder. But maybe? Would that? No, I don't. I want to see that implementation. But where's it coming? Just can you look that up? Yeah. Were you looking at the repo with 335 stars?
Yeah.
Oh. Interesting. So, dude, this code, looking at this code hurts me so much. A lot of very academic and very institutional AI researchers have no idea on how to code. It's really, really depressing.
Yeah, it definitely looks like it's a separate package. I'm guessing it's from the OpenAI gym environment.
Dude, so the actors and the critics are literally just linear layers and ReLUs? Is that it?
And convolutional if there's an image involved.
I thought I was thinking something completely different. I thought there were like some weird modified like attention mechanisms that learn like
No, they're pretty basic. Like, I mean, it's all here. It's all like 16 filters. Like, it's tiny.
that's pretty simple. I guess I'm just overcomplicating stuff. Do you really like RL? Like a lot? Is this something you're
I wouldn't say that because RL usually doesn't like work robustly. Like, there's a lot of little hyperparameter tuning things that you need to make it work robustly. Sometimes it works and sometimes it doesn't. It's not like supervised learning or like language model training where everything works like as expected every time. So it's definitely interesting. I think it's like definitely has more complexity than supervised learning in my experience, but I wouldn't consider myself an expert on reinforcement learning or say that like it's like the end all and be all of AI.
You said hyperparameter tuning. Is that a big time investment? Or is that like a big problem now?
Yeah, I mean, these networks are just like, they're not like, it takes a long time for this to learn. Like this algorithm like takes a long time.
So what's better? What's faster than this?
I mean, hindsight experience replay seems a lot better, but
Hindsight?
it still takes a long time. Like there's no reinforcement learning algorithm that behaves as like robustly as supervised learning algorithms that I know of.
Why not? Is it the environment?
It's just a harder problem that you're tackling. I think control problems are usually they just require a lot of samples.
Why?
Because you need to gain like spatial intuition, and because of this bootstrapping thing that's going on, like you don't have labels, right? So it's almost like unsupervised, right? You just have a slightly better guess of what the quality of the state is, and there's statistical issues with this, like that double DQN addresses, and yeah, but it doesn't fully address them, so it's kind of, yeah.
Then what would be the future of reinforcement algorithms? I want you to depict the perfect RL algorithm. What would it look like?
I would say something that integrates like on some very deep level with a language model that understands, that also has like some spatial understanding. Like a language model given an image, like a vision language model given an image, knows that this is going in the direction of accomplishing the goal versus not accomplishing the goal, right? this algorithm on its own, like, doesn't have any idea at the beginning, but the language model already knows these things, right? So you get you get a speed up that way. Something cool we could do.
What would the algorithm look like?
It would be something like, okay, one way to do it is to have a reinforcement learning algorithm that then checks with a language vision model, and if it's going in the direction of progress, then it gets rewarded, and if it's not going in the direction of progress, then it doesn't get rewarded. So I guess the language model itself would be like the reward function. So that would be something cool to work on.
Wait, can you say it again? I'm writing this down. RL algo that checks with the vision language model to check whether progress is being made. If yes, reward.
Yeah, and rewards.
If no, not reward.
Yeah. So the way you usually talk to a reinforcement learning algorithm is through the reward function. So you can always make a reinforcement learning algorithm better by giving it better rewards. And so if you have a good idea at every time point, whether you're doing good or bad or better or worse, then you can provide that feedback to the reinforcement learning model, and it'll learn a lot faster. So reinforcement learning with language models, language vision models as a reward function.
Say that again, that last part.
Reinforcement learning with language vision models as a reward function.
What would they be outputting?
The language model, just a number corresponding to how close, like what the reward is, basically, like whether it's positive or negative. It's like kind of like playing hotter or colder.
So let me get this right. You're saying you have a base LLM, right? And then you have a vision model as a reward, or a language model as a reward for the vision model.
You have a vision language model that takes in images of where the reinforcement learning algorithm is going, and then it predicts, like maybe it takes a stack of images as well, so it can see where it's going, and then predicts whether that's good progress or like bad progress, whether it's getting warmer or colder.
Can you write this down, please?
Yeah, sure.
Put it in the papers thing that you made.
Yep.
Yeah, that'd be interesting. I'm definitely.
Why don't you just fork Open Assistant and then add the image component and let people up and downvote good or bad answers, and then you generate your model from the good and bad answers, or the upvotes and downvotes, and then you take that model and you feed that back as the loss function after you go through the inference part.
Isn't Open Assistant, wasn't it taken offline?
I don't know if you mean the website or the GitHub repositories, but I don't see any point in keeping the website running now that the project is mostly done, or should be done anyways. Since I'm not actually hearing a task, like if you had a task, then you'd have to design your RL around the task, like picking up blocks. But since it sounds like you don't actually have a task, you just want whatever people think is right or wrong. So it sounds like you need something like open assistant and a bunch of people to rate.
Yeah, that would be a good idea.
So what we need is like a vision language model that we can run for free without getting throttled.
The ones
And without breaking Microsoft terms of service.
Well, you've got my compute.
yeah. Do you think how much VRAM do you have, Zach? In total?
866.
866
But I'm having issues getting it working.
866 gigabytes. You heard that, Dimitri?
No.
What do you think we could do with that?
I have like GPU, I have like 6.
Do you think like we could do something with that for RL?
Oh yeah, for sure.
Are you talking about a Gaudi 2 8 GPU instance, or what are we talking about for hardware?
Zach, would you like to?
Yeah. Tesla K80s.
A lot of them.
Okay, so you must have several of the GPU servers, right?
A lot.
36 Tesla K80s, and then 3 servers. So not a ton. But we could definitely run that RFL thing.
Could we do this? So like, we should implement this for Call of Duty.
We should implement this for Rise of Sparta.
Oh, that's right.
Rise of Agora, I
Break
mean.
into the military-industrial complex?
What was that?
Are you trying to break into the military-industrial complex?
No, I just think it would be funny. I used to make aimbots when I was a kid. I just think I think it would be really funny if like just making aimbots that are like really, really insane. Like the best. They're better than like 1,000 times better than any human player. Like they could just shoot
for like ruining my gameplay.
they could just shoot like a lamp pole. Like imagine it just shooting like a lamp pole and it just hits 5 people with like a ricochet or like something ridiculous. That's what I'm trying to see. That'd be really funny.
I did have a project similar to that with ricochets.
For Call of Duty?
Oh no, not Call of Duty.
Dude. Yeah, I think true AGI would be just like quick shotting everybody in like Modern Warfare.
Yeah.
Okay. I'm going to close the presentation now. If there's no more questions.
Yeah. Could you like share like all your ideas for the vision language model thing in the channel or the post that you made?
Yep, I'll elaborate on it.
Yeah, go deeper on that.
Thanks,
because
Nature.
I think it would be very valuable.
I'm gonna go through that.
Yeah. Well, thanks, brother. Appreciate you.
Hey, Kyle, so you are done here and you take a bathroom break and, coffee break or whatever. Can we get into a voice channel?
Oh, sure. Yeah.